to the working group meeting. As some of you may be aware, we are currently working on a proposal for a ROSCON workshop. If someone's interested to help, please get in touch. But other than that, we don't have any big working group activity. But we have a guest today, which is Taneli Korhonen from the company Karelics. And to be honest, I just found their product or their open source project on LinkedIn and thought it would be very interesting for our working group. And luckily, they have agreed to present it to us today. So thank you very much for being here. And I think I would give the word to you. If you can try to maybe share your screen.
Yeah, thanks for having me. Let me get the presentation mode, and it seems like I don't have rights to share my screen. Only organizers and presenters can share, so maybe you need to give me. Right, now it looks better. Then just select the correct. Oops. Find the right screen. It's always the last one that you look for. Okay, there we go. So, task manager. Let's see what it's all about. So I will start by talking a little bit about the problems that we faced and why we ended up coming up with the task manager. So these are some of the problems that we faced when developing the Karelics Brain, our software for autonomous robots. And these include triggering tasks that the robot should perform from multiple sources. So the robot may have multiple user interfaces. Maybe it has an integrated touchscreen, or there's a fleet management software, and maybe it can respond to voice commands, whatever you can come up with. And there's of course then possibility that it may receive commands from any of these sources, and those all need to be handled correctly. And then also it would be really nice to track all of those tasks and display them in the UI correctly, regardless of where they were started from. And it would be nice potentially to react to all of those different tasks somehow. So if the robot has a speaker or something and you want to display sound signals, something like this. And of course, then, like I said, if the tasks requests are coming from different sources and they can be conflicting somehow, maybe there's two tasks that are different, but you shouldn't perform them at the same time. You need to handle this somehow. And then we would like to perform more complex tasks and missions that can combine of various steps of different types. And in our case, we are aiming the robots that we're developing software for are potentially working on construction sites, and so places where internet connection can be unstable. So all of this should ideally be possible with limited connections, let's say. Probably when you give the task, you should have at least some control of the robot, but then it should be able to perform it autonomously after that. So we came up with Task Manager for this, and the main features of it are as follows. So it offers a single interface for starting all tasks. So you can start basically whatever functionality the robot has, have it be performed via the one given interface. Then it publishes information about all the tasks that are being performed and their results, so that you can monitor them from also elsewhere than where the task was started from. And then it allows you to define a group of tasks that are blocking so that only one of them can ever be performed at a time. And then for the last point or problem, it allows giving a list of tasks to perform as a mission, and then handles performing the whole mission so that each task is performed consecutively after the previous one. And then as a kind of a bonus feature that wasn't really the main problem in the previous slide, but it also implements a global stop task for stopping all ongoing operations. All right. So basically, as from the picture and the bullet points, you can think of it acts as an interface between all the functionalities that the robot has and any user interaction methods that the robot might have. So then let's briefly check how you would use this. So first of all, as in the previous slide we saw, there were ROS actions and services. So you of course need to have the functionality that you want to use as a task, and Task Manager allows you to declare any existing ROS2 service or action as a task. And once this is done, you can then start these tasks by calling this special action, Task Manager /execute task. And this can, of course, be called by any ROS node that just has a client to this action server. Then these statuses can be monitored from active tasks topic. So once a task starts, it gets published to this topic that this kind of task is ongoing, and its status gets updated when it changes. So from the upper diagram here, you can see this, that there's a client that calls the execute task service, and then both the client and any outside observer node can monitor how this task is progressing, at least in the main points. So of course the client can get an additional information via the action, but the status and results can be monitored from elsewhere also. And then in the lower diagram, you have the mission concept. So you can call a mission as a list of tasks, and then the task manager figures out which services and actions it needs to call and calls them in sequence, and returning the results of each of the subtasks, and then the final mission at the end. And then finally, you can cancel any task that is cancelable by calling the cancel task service, or you can call all tasks that are designated to be cancelled on stop by calling the stop service. Right, going into a little bit more detail about tasks. So what are they? Already mentioned that they are essentially existing ROS services or actions that are just transformed into a task. And when you declare them as tasks, you can give them a few properties. These are the ones on this slide. So any task can be set to be blocking, and this means that it is put into this special group where only one of these tasks can be executed at a time. And if a new task comes in, then the previous one is cancelled, or we waited upon if it is not cancelable. Then you have a cancel on stop flag, which means that if you set this to true, then calling the global stop task will try to cancel this task. And single call or reentrant is kind of the same as blocking, but for the same task. So if the task is not blocking and it's something that you might want to potentially run many times in parallel, then you can set this flag to say that the task is re-entrant. And the final one is reporting cancel as success. This is kind of a more niche property in that it is reserved basically for tasks that can go on indefinitely until a user decides to stop them. And in this case, usually the stopping is done by calling cancel, but since the task manager then reports the end statuses, it doesn't really make sense to report this case as cancelled, but it should be rather reported as success because the user just decided that, okay, this is enough and the task is now ready. Then let's go to check a little bit about how to call a task. So already mentioned before that it is done via this execute task action. And this is the information that you need to provide to it. So previously you will have already defined the task, and now you should start it. And to start it, you can give a task ID if you already have one in mind that you want to know and predefine basically. This is basically a UUID as a string. If you don't provide it, then it gets generated automatically and given to you in the actions response. You should define the task name, which should match the name that you have defined the task with when declaring it. Then you can give a source. This is just for convenience, maybe for the UI to display where this task was started from and this kind of stuff. So it can be any string basically. And then the request information. So this task data, basically the ROS actions or services request or goal in JSON format. And then once the task is ready, the result gets returned to you as normally with actions. And this information contains the task ID, the result again in JSON format, and the end status of the task. And if there was an error, then there are a set of predefined error codes that get returned also. Okay. Then briefly checking how you can track the tasks while they're ongoing. So regardless of where the task was started from, while it's ongoing, it always gets published to the active tasks topic, which basically contains a list of all tasks that are ongoing. You can see here on the upper picture what it looks like if you echo that topic. And from this, you can basically then monitor whatever the robot is doing from any node and implement some custom logic on top of that if you want to. And similar to this, the results, whenever a task finishes, are published to the task manager / results topic, and in the JSON format, the same format that the execute task action returns to the client. So yeah, the point of this again is that you can monitor the robot's work from sources other than what is giving the instructions and goals. Then we briefly take a look at missions. So missions are just combining several tasks into one. And basically what you do is from this picture here. So if you have two tasks, let's say navigate and spin, and you want to perform them in a sequence, you can define any sequence of them and then just give this one sequence to task manager and it will call all of these consecutively. until the whole mission is done. And the results of these subtasks get published to the results topic, and their performance or statuses to the active tasks just as the same as regular tasks. In addition, for this parent mission, the status also gets published, but the result of the mission does not contain all of the detailed results of the subtasks, so those you should pick up from the results topic separately. And the point of this is that we can now, with this, have the robot perform some complex mission, even so that it only has internet connection at the start when you give it the task, and probably at the end when you want the results. But all of the bulk of the mission can be in a space where you don't have connection to the robot at all. Then canceling, quickly stating about the two different forms of canceling. So I think I already kind of went through this earlier, so won't dwell too long on this. So, but you can cancel any task by canceling this service, assuming that you know its task ID, which you can monitor from the active tasks topic, for example, as long as the task is cancelable. So, for example, of course, services are not cancelable, so those ones you cannot really cancel. If you try to cancel them, then there is a set timeout that will be waited. So if the task finishes within that timeout, then I think you get returned success on the cancel request. If it doesn't, then you just get a failure from the request. And the point here is that the cancellation does not have to come from the same sources where the task was started from. So normally with actions, only the client that requested the canceling has the easy access for canceling that tasks. But in this case, it doesn't matter where the request comes from. Of course, the client can also cancel the task in a normal way via the goal handle as well. And then this global stop tasks again cancels all active tasks that were marked to be cancelled on stop. And here is a brief list of our future plans. Will not comment anything about the time when these might be coming. They are not. I don't think any of these is currently in active development, but these are some of the ideas that we've had for future improvements. So pausing and resuming tasks, queuing them, prioritizing them. In case you get conflicting tasks, should you wait for the previous one? Should you cancel it? Then tracking start and end times, and also possibility to declare tasks at runtime instead of only beforehand in a YAML file like it is currently. And then potentially scheduling them as well. Then I have a short demonstration. So for this, let me find the predefined terminals that I have. So let's start by let's actually look first at what we have in the demonstration. So here is the configuration file for the task manager. We declare two tasks, navigate to pose and spin. And navigate to pose, here we define the task name, the topic that needs to be called, and the message format of the task. And then we set this one to blocking, same as the other one. And both are also set to be cancelable on the stop command, and neither is reentrant. The second task is then the spin, has basically the same information. So these are both now from navigation 2. Then what we have a simple node for tracking the tasks. So what this one does, it simply just subscribes to the active tasks topic. And then in the callback, whenever it receives a message, it prints the list of active tasks and the statuses, how they are. So this all is just to make it human readable, because of course the enum is not necessarily that nice to read otherwise. And then we have some helper scripts that just sends a task request. This one just calls the system stop task and then prints the result when it's received. And then there is a mission, which this one actually just calls the stop task twice, kind of a funny mission, but for demonstration purposes to keep it simple. So where was the, yeah, so here you just set the same subtask twice and it gets called twice in a row. And once again, we then print the results. Then the final example is a little bit more interesting once we get to it. So we will be using the Turtlebot 3 simulation for this. We will be calling navigate to pose and spin 4 times in a row, this sequence. And before that, we're calling the spin task twice, or no, we're first calling navigate to pose and then spin, which should then override the first task. Okay, now let's get the task manager running, and then I will here I should have the tracking, listening of the tasks. And first, if we send a single task request, we see that we just finished get the done status immediately. There was, of course, this was the stop task, so there was nothing to stop. So it finishes with a success and quickly. Then if we send a mission, this was the 2 stop tasks in a row. The output looks a little bit different, but so we get the mission status and then subtasks. So we also get the subtask statuses in the response, but the results you should have actually I should have had a terminal also listening to the results topic. Missed that one, but the more precise results would be there if there were a need to see. Then let's get the simulation up and running. We'll have the gazebo here on a different screen. Let's clear this out a little bit so there's not as much clutter. This is actually nice to have, so let's keep that. All right, and then if we call the example mission that we had, so calling the first navigating somewhere, this is actually not a mission yet, and then calling a different task, different blocking task cancels the previous one, and then we sent the mission. So now it's performing the mission, and you can see that here we already are done. So we now don't need to have any connection to the robot anymore. Now it's just, it could be going to an area where there's no connection whatsoever and performing these tasks on its own, assuming that the robot is otherwise capable of that, of course. And here in the active task list, you can see whenever a subtask finishes, this updates. Same would be for the results topic. And task manager logs, of course, also print that information out. And there the mission, the entire mission finished. Okay, that is it for the brief demo. And I think it's time for questions if there are any.
Yeah, cool. Thank you very much. Are there any questions? Okay, so I guess I have a couple of questions. You mentioned that that you mainly use this, or as I understood, you mainly use this for construction robots on construction sites. So this would be generally the use case where you kind of have an operator that at least from time to time goes to the robot and then kind of sends these tasks to the robot, right? Or or do you think this would also work for a use case where you want the robot to operate more autonomously for a longer time?
It could it could work for both, and we actually in our system we run all of the tasks that the robots get via task manager. So we basically use it for everything, whether there's just a simple task to navigate somewhere, it goes via task manager, or whether the robot is driving back and forth the whole day between two positions and waiting for some vocal voice cues or other signals at certain points. All of this you can do with task manager. You just, if you want to navigate somewhere and wait for a time, you need to have the wait task, and then that's it. You're done there.
Mm-hmm. And do you also expect your customers to provide these tasks, or is this something that you would normally deliver with the robot, the task descriptions? Or the task definitions?
I can answer.
That's a good question. Yeah.
It depends on whom to count as the customer. Yeah. So if the customer is robotic manufacturer, in this case, we expect them to know better what to do. So if it is a painting robot, then do painting and expect some metadata to be delivered to you. But for some other, like we can extend, if it will be a combination of both robots, so we install a painting robot on top of or a hand robotic arm doing some stuff, drilling, for example, on a robotic wheels, then we can have robotic wheels operatable tasks and then get some of the tasks from the robotic arm, or robot painter or whatever. So basically, yes, we expect them to know their business a little bit more and then provide us with those. Taneli, here I might be slightly incorrect because they can provide the actions and services, and we can support the tasks that need to be called. And from the very end customer, from the construction sites, it comes slightly differently. So they expect certain behavior to do a certain job, and then it is the matter of the mission already to be like defined and then to be split into the sequence of certain subtasks, or tasks under the hood. And important from the roadmap is of course the pausing of the mission, and like pause, go to charging station, do charging, or like pausing of the mission when you need to do the intervention from a human with teleoperation if that's needed. So it works autonomously to the end place, but at some point you need to stop it, do something like take a look into the camera. You saw something on the camera and wait, let me zoom in. Yeah, so do some additional tasks while it's waiting. So it's all kind of adjusting the mission, and mission can be interrupted if the charger, like the battery status, is not enough to complete the mission. Yeah, then the charging set of charging tasks need to be added in the runtime. So it depends on the use case. Yes.
Mm. So would you then also do something where you, for example, monitor the battery state, and when you recognize the battery is below 20%, you automatically send this charging task?
It is planned. Yes.
Okay.
To be done this way. Yes. Therefore, these pausing tasks were first actually in the line of to be supported.
I have a question.
Yes.
You hear me? Okay. So right now it seems to focus a lot on the happy path, saying that you can make a mission that has a sequences of things, right? And then you assume you can just do them one after another. And then what a lot of technologies that are presented here do is they implement some sort of decision strategy, right? Like behavior trees, for example, or finite state machines that say like, okay, if this went wrong, we want to do this other thing. Do you have anything concrete in mind that you want to do?
Let me just clarify. So you're asking about like fallbacks and these types
For
of
example,
things. So,
yeah.
Yeah, in the current form, Task Manager is not very well suited to this. It is something that we have been thinking that it would be really nice to have these branches where if this one task of the mission succeeds, you take a different path than when it fails, and certainly like behavior tree type solution could work for this, but we haven't gotten to do that yet because we haven't really found that big of a need for it in our use cases. But certainly it's something to be considered going forward.
I will add maybe one additional point. So we try to also put some additional meta information that the service that is executing the task should have this meta information to do the autonomously the task. Like for example, if you do the photo documentation mission and you cannot reach certain position, then skip position instead of like stopping the complete mission. Yeah, because like it's an error. No, you just skip and go to the next one, to the next task. So this is an example of additional meta information that can be provided into a mission when it is, and then from the mission into those single tasks that are decided and then given further. And then of course the behavioral tree is happening on the task execution level. But it is a valid input. We just didn't have this example yet where we need it.
And then I guess another thing that people find as a need at one point, once the complexity is increased, is like some sort of shared information sharing or some information sharing, right? That you have some sort of behavior trees. It would be a blackboard or a world model or some sort of like information store.
Yeah, so as far as the storing of information goes, we haven't been thinking task managers specifically for that. It would probably ideally be some other node that listens to what happens in task manager and then stores these statuses. You can kind of the current tasks and everything you can track from the active tasks topic, so that is kind of our version of that. It's quite bare bones compared to something like a Blackboard, but it has been more than enough for us thus far.
Yeah, you can't do all the things at once.
Yeah, of course not.
Cool. Thank you very much.
There's also a question in the chat from Enrico. I will read it out if that's okay. From a deliberative perspective, can the fleet of robots be considered a single robot with multiple components acting concurrently and managed by the task manager? Or are there fundamental differences between the deliberative systems of a single robot or multiple robots? I don't know if I made this worse by reading it.
Yeah, I think so first of all, I will say that the task manager is, at least from as far as we have been using and designing it, it has been designed to work on a single robot rather than as a fleet controller. So from our point of view, task manager should be just, it handles the tasks that are coming to that one robot. But on the other hand, if you have a fleet management system that works via ROS, and if your robots are simple enough that they can be easily managed by just a reasonable sized set of actions, maybe you have just separate topics for each robot's actions so that you can differentiate between them. You could use Task Manager to control those, but I do think there are probably, I would think that there are better alternatives out there for that, though that is not my specialty field, so I don't really know that much details on that side. But in theory, it should work if you wanted to use it like that.
Yeah, I guess you could. Ideally, you must make other considerations if you really want to consider a fleet. Then I think Calvin, you raised your hand.
Hi, can you hear me?
Yes.
Oh, okay, great. I find it interesting that you are also considering what do you call it, the blocking tasks and non-blocking tasks. I guess that stems from the limitation where, for example, in simple action task interface, then sending the same goal will preempt the previous goal. I guess that's also one of the reason why you implement this, I assume. But I wonder, why do you do this at a task level instead of a resource level? For example, if you have a manipulator on a robot and your robot has wheels, so you have two completely separate independent tasks. One just needs to drive, the other one just needs to move the robot. So they don't. So one task will not. The other one just needs to move the arm. So these two tasks are independent. They will not be blocking each other. However, if you have the third task that let's say it needs to home the robot, so the homing all the joints and homing all the wheels. So this has the dependency between. This causes dependency between the arms and the wheels. So I wonder if you have, if you make all of a sudden make homing task a blocking task, that eventually you cannot maybe move the arm while moving the wheel at the same time, because through the dependency they might all be blocking each other. All the tasks might just be blocking each other.
Yeah, I understand the point. This is something that we have considered, and it is a currently it is a limitation of the system that we have. So I can tell you where the idea of blocking tasks comes from. Basically, we have this kind of a multi-floor navigation system as part of our brain, where you can have the robot map a series of maps, and on different floors there can be elevators or stairs or slopes in between to navigate between floors. And then what you need to do in order to navigate between these, you of course need to drive to a certain point, then switch the map then drive again, switch map again, navigate again to the goal. But then so this is something that you should be able to do. But on the other hand, if you're just navigating somewhere, you for sure should not go and change the map while the navigation is going on if you are wanting to stay on the same map. So the blocking tasks were implemented on our side to prevent these conflicting tasks of different type again. So like navigating somewhere and changing the map while going there. This should not happen. But on your point about there being maybe two tasks that are not conflicting, but then a third task that can be conflicting to both of those is a very valid one, and we've thought of that. So I think this improvement point was actually missing from the last slide, but we have also considered making kind of more of these blocking groups. So you could, in this case, you could have one blocking group that prevents this driving from conflicting with the homing, and then the second one for the other pair. And maybe this one task could even belong to both groups, then the one that's conflicting with multiple different tasks. And this would be a solution for it. And we have it kind of in our backlog. But again, we haven't gotten to it yet because there hasn't been big enough pressure on our use cases to have it.
Thank you. I just want to share how I ran into similar situation. In my case, I was using behavior tree, and sometimes with a lot of subtrees, and when you're running concurrent, like parallel tasks, you might end up running, like calling the same action client in parallel, and the second goal sometimes, well, most often will cancel the first goal, and then that leads to the first parallel branch going to a weird, some other weird state, weird branches, and usually that is quite an undesirable behavior. So what I did, as well, usually one of the leaf, or usually action tasks I implemented as behavior tree leaf nodes, and what I did was allow the node to be configurable such that if it is connected to the same server, then you have an option to preempt or not to preempt the same goal, the goal. For example, so you can implement in a way that you're queuing up the goal. So if you know the action server is busy, then you have an option to just wait until it's done with the previous goal, or you can configure such that you can send a new goal anyway, and then that will preempt the first goal. So there's also a grouping at, I guess, at the behavioral tree node levels then, in my use case at least.
Yeah.
Thank you.
This sounds similar to what we have in mind with possibly prioritization of tasks and this queuing probability. The big question then becomes, how do you configure it so that it's easy to configure it any way you want, and that's something that we haven't really thought too deeply of yet.
Mm-hmm.
But yeah, the idea sounds very similar, and we have already seen some examples where this kind of thing would be very nice. Like I said, currently the way Task Manager works is it just cancels the previous one when a new blocking task arrives. If it can be cancelled, then this is for sure a current limitation that hopefully we can remove in the future.
Thank you.
Okay, so if there are no other questions, thank you again for the nice presentation and for sharing your work. I think I put the link to the open source repository already in our minutes. If you could also send me the slides later, this would be nice, then I could also add them there.
Yeah, sure. Thanks for having me.
One other note that I just wanted to tell everyone is that this working group is now a community group. That's basically on the back of the changes of the OSRA. I don't know who has noticed this so far, but the ROS governance model has changed, and I think the reason was that previously technically working groups were part of the TSC, the Technical Steering Committee, and so you could then have official working groups which were part of the TSC, but ours was a community working group, so a non-official TSC working group, and they basically changed the name for those now to simply community group, which means we work less and are more of a group. I don't know. It's just a different name, and I will probably also, in my mind, it will probably keep being a working group. And I also left GitHub organization with the WG in there. So yeah, not much changes, but in case you're wondering why it's now called community group, that's the reason. And also I'm not going to change the logo. Okay. With that, thank you everyone for attending today's meeting, and see you all in 1 month, I guess. Bye.
Thank you very much. See you. Bye-bye.
See you.
See ya. Thank you. Bye.
See you. Bye bye.